Hey everyone. So today we're going to be doing the density lab with KoolAid. Now I have here some pink lemonade KoolAid powder. I have a 100 milliliter volumetric flask to bring the KoolAid up to drinking strength. And I've got a funnel for putting the powder into the volumetric flask, and I've also got some more glassware, but that glassware is not here. That glassware is next door where most of the lab is. This part of the lab is the part that actually includes the analytical balances. Now the reason I don't have the rest of the glassware with me is because while I could hypothetically do the entire experiment right here, this is supposed to be preparation for working in an actual lab in the future. And usually the analytical balance is something that lots and lots of people need to use. So you do what you need to do near the balance, and then you get out. Now, with this analytical balance, you can see that we have doors on the sides that we can open and close, and on the top that we can open and close. We want to make sure that when the balance is in operation, the doors are closed so that we don't have air currents changing the apparent mass of our sample. And we have this layout right here. So what I'm going to do is I'm going to re-tear this. There we go. Now here, 0, that's the tear button. This is the mass that it's currently reading since the last time it was teared. This is the maximum mass it can handle, 120 grams. And this, the D, is the, that is the, how do I put this? That's the uncertainty. So this balance is accurate down to 1/10 of a milligram. Now, one of the things to notice about me is that I'm wearing gloves. A lot of the time, gloves are good at protecting you from the chemicals, but a lot of the time, gloves are needed to protect the chemicals from you. In this case, I want to make sure that the moisture and oils on my hand do not get onto the weigh boat that we're going to be weighing and change the measured mass. So, here we go. Now, I did the unit conversion to figure out how much KoolAid powder I would need to bring this up to drinking strength. So this is a volumetric flask which holds 100 milliliters of solution with an accuracy of plus or minus 0.16 milliliters. And so I've done that conversion, so I need 0.380385 grams. Now it's important to note that because the uncertainty here is 0.0001 grams, I only actually need 380 grams. The last digit, I want to get close to about 3 or 4, but that, because of the uncertainty, that isn't as big a deal, and the digits that come after it really are not that big a deal. Again, because of the uncertainty. So, let us go. Opening that up. weigh boat on there. Alright, so now we re-zero it. 0 grams. And what we're going to do is we're going to leave the weigh boat on there while we add some of the pink lemonade. This is a scupula. It is really good at transferring solids from one place to another. It doesn't have a whole lot of other uses though. And I'm using it because obviously I need to be able to move amounts that are fairly small. If I just tried to, pour it on there, then it would be very, very easy to overshoot. So here we go. These grains are really sticking together right now. Feels almost like sandstone. So I'm at 0.2696 right now. Point 3007. Point 3674. Point 3772. Coming up on it. Point 3812. So I've overshot it a little bit. Now, when you overshoot, oh, no, wait. Went down. So let's make sure that the air currents aren't affecting anything. No, 0.3811. So that's still a bit too high. Now, when you go and take the sample out and remove some, you never ever put it back in the bottle, because now that the sample is on there, you're hoping and you're trusting that that weigh boat is clean, but it's not going to be as clean as the inside of this vial. So instead of taking it and putting it back in the vial, we take it and we dump some into a waste container. And then we see what we have. Point 3780. Now it looked like it was only a few of those grains that left to bring it down, so I need to be careful and put very, very few grains back in there. .3784. Come on, you. Point 3796. Okay. 0.3797. Okay, so we want 0.0007 more. It's going to be a very small amount. .3800 now. Another very, very small amount. .3802. And I'm just going to stop right here, because if I keep going, I'm liable to overshoot again. Yeah, if I keep going, I'm liable to overshoot again, and then I'm going to have to, dump some more out, then add some more back in, and you can drive yourself crazy constantly doing that. But so I'm going to be okay with 0.3802 plus or minus 0.0001 grams. And this is within something like 0.5% of what we're going for. So that's plenty good enough for this experiment. So now I'm going to take that out, and I'm going to transfer that powder into this volumetric flask. You might notice that the volumetric flasks that are stored with their glass stoppers have a piece of paper in between the flask and the stopper. That's because if you don't do that, then any temperature fluctuation could cause the pressure in here to build up and pop the stopper right off, and then you might end up with a broken stopper. So that's there. Now, next what we're going to do is we're going to transfer the powder from there into the volumetric flask. And one of the things to be wary of here is static electricity. Sometimes, especially if you're working with some metal tools around glassware, it's really easy to accidentally build up static electricity, a static charge right around here. And if you do that, then just pouring something dry directly from here into there, the static electricity will cause some of it to stick to the rim and will cause some of it to stick to the outside of the rim. And that's really annoying to deal with. So you don't want to do that. You want to add with a funnel. And here we have an issue where, because it's a powder and this is a somewhat narrow funnel, it doesn't want to go down. So we can rinse it down with DI water. Now, it's important to note that the DI water is okay to use to rinse in this case, because DI water is what I'm going to dissolve it in anyway. If I was going to dissolve this in something like acetone or alcohol, then I would be rinsing with that instead of DI water. Okay, so there we go. Now I rinse all the rest down just like that. And here we've got a situation where don't know if you can see it there. A bunch of the Kool-Aid powder is stuck to the whey flask. Now I could use this to try to scrape it in, but I don't want to do that if I can avoid it, because I don't want to accidentally scrape in some of the plastic along with it. So instead, because the plastic here does not dissolve in water, and I'm dissolving this in water anyway, and I've got quite a bit of water that I need to add anyway, I'm just going to rinse it in with the DI water. Okay, so this is still a bit wet, but it doesn't have any of the powder in it. Now I mentioned before that you want to only do as much here, as you actually need to do. And the argument might come up, well, but did I really need to put the Kool-Aid in the volumetric flask here? The answer to that is probably yes. Chemistry labs are very well ventilated. They have to be, because a lot of the chemicals that we use are corrosive or toxic or otherwise dangerous, and also they evaporate. So we constantly have the ventilation system going in order so that any vapors that could harm us get sucked out of the lab right away. But what that also means is that there's an awful lot of air current in the chemistry lab. If you try to take a solid in a whey boat and transport it from one part of the lab to another, it's really easy to accidentally have one of those currents blow it out of your whey boat. That has happened to me. So that's why we made this here. Hey, so we're back. We're in the main part of the lab now, and I am adding deionized water to bring the Kool-Aid solution up to 100 milliliters. Now, while I'm continuing to add this, I should point out the rest of what we're going to be doing. We are going to be pouring this Kool-Aid solution about 5 milliliters at a time into this graduated cylinder. Then we're going to measure the volume of the solution in the graduated cylinder. And after that, we're going to transfer it into some weighing vials. Now, what we're using is some scintillation vials, like this. You can see I've already labeled them with Kool-Aid and the sample. Now, the procedure says do 3 of these, but I'm doing 4 just, in case one of the data points goes awry. And one of the things that I need to point out is that I labeled these before I weighed them. Now, I already got the mass of all 4 of them, and it's important to label them first because, ink actually does have mass, but also it's important to keep track of which is which, and that is right down to keeping track of the lids. The reason I bring this up is because even though these scintillation vials look like they're all the same, it turns out that of this set of 4, the vial with the most mass had 0.3381 grams more than the vial with the least mass. And given that 5 grams of deionized water is about 5 milliliters of deionized water is about 5 grams, you can understand why being off by 1/3 of a gram could throw your density calculations by quite a lot. So here we go. Now, with this volumetric flask, the solution is 100 milliliters when the bottom of the meniscus right there is at the same level as that line, which is drawn all the way around the flask. So when you get to the end, you need to pay really good attention to what you're doing. There we go. You need to make sure it's just right. So if I take this and I start pouring it into the graduated cylinder, and I just start the experiment right now, I'm going to run into a slight problem. And that problem is that this solution is not very well mixed. The color is the most powerful, is the darkest on the bottom, and on the top it's essentially clear. So what I'm going to do is I'm just going to go ahead and put the lid on this. I'm just going to shake it around very gently. Now what I want to do is I want to actually invert it, but I need to be careful that I hold the lid on well so that it doesn't end up coming out the top. Okay, that looks pretty good. So it's still more see-through on the top than it is down here, but that's because the top is thinner. So it's a shorter distance to see through. At this point, the whole thing is pretty well mixed. And I can smell it. I could not smell it with the cap in, so that's reassuring. Now, when pouring this into the graduated cylinder, need to mind the lines, the markings. I also need to use a funnel. Funnels are not always necessary. However, when the opening you're pouring through is pretty close to the same has pretty close to the same diameter as the thing you're pouring into, and in this case, I think it's actually a little bigger over here. Then it's really important to use a funnel because the chance that you will spill stuff is way more likely. Also, with this kind of funnel, we need to make sure that the edge here does not become airtight or watertight. So I'm going to just lift this up slightly while I am pouring. Now the goal here is to get about 5 milliliters, but one of the things that's important to keep in mind with chemical analysis experiments is that getting the exact amount that you're looking for is a lower priority than knowing the exact amount that you got. So if this is slightly above or slightly below 5 milliliters, that is not a big deal, as long as we know how far above or below. So here we go. Now, looking at it there, there's the 5. The meniscus actually appears to be exactly on the 5. I cannot tell if it's, yeah, no, as far as I can tell, it is not higher or lower. So that means that we got 5 milliliters in there. and we transfer this into scintillation vial number 1. And here, one of the things I'm going to do is I'm going to take, so graduated cylinders have a lip where it's, in order to make it easier to pour out the liquid. So I'm going to go ahead and I'm going to touch that to the inside of this glass here in order to make sure that the liquid is less likely to splash, and also in order to make sure that when I'm down to the last drop is going to end up right there. So I need to make sure that it transfers. There we are. You need to be very, very cautious when shaking one piece of glassware near another. It is very easy to accidentally knock them together. There we go. Also, with that last drop, you need to be very careful to get it on the inside of the lid to make sure you don't lose any. There. Okay, so what we're going to do is, in order to minimize the time at the analytical balance and the time running back and forth, we're going to do all 4 of these right here. And then we're going to weigh them all at the same time. Now, because the markings on the graduated cylinder are every 1/10 of a milliliter, I eyeballed that last one to 1 digit past that, but because that digit was 0, I ended up with 5.00 milliliters. Come on. Okay, this time we way overshot it. Also, because the water can evaporate, I always put the stopper on in order to make sure that the concentration does not change, because the water evaporates but the powder does not, at least not at room temperature. Okay, so as we can see here, we've got significantly above 5 milliliters. Now let me get the camera level with the ground. And when the line goes straight across, we know that it is we know that this is level 2. Okay, so that looks like 5.7 roughly. Let me eyeball it. .76 milliliters. That is going in vial number 2. go. Okay. You can do it. It doesn't really matter. Okay, so that's 5.18. So I overshot it slightly. See right there. And then number 4. So this one, I only overshot very, very slightly. That is about as close as we can get it while still slightly overshooting. So I'm going to put that at 5.01 milliliters. anything left at the end there? Nope. Okay. So now we're going to mask these again. So we're back in the analytical balance room with our analytical balances. Here we've got our samples. Now, one of the things to bear in mind with using these analytical balances is that the 0/tare button, that can be kind of tempting. And what I mean by that is it can be tempting to simply tear a piece of glassware, then go and get your sample and come back and put the glassware back on and assume that 0 is still in the same place that it was before. But that's not always the case. See, as the day progresses, doors get opened, doors get closed, and also the chemical hoods, which are connected directly to the vent systems, they get open and they get closed. So throughout the day, because of that, the ventilation in a room can change. And specifically what I mean is they can change the air pressure in the room. If there's more air pressure, then the air actually weighs more. And that includes the air that's inside here on top of our balance. So because of that, you never want to trust a tare or a 0 for more than about a minute or so. And especially not if you're working in a lab with a lot of other people, because someone else might get in there before you and re-tare it, and then you're just, up a creek. So that's why you always want to write down the masses first, and then come back and re-tare each time you use a new, each time you take a new measurement. Another reason for wanting to take these measurements quickly is that sometimes there's moisture on the outside of a glass. There's always some amount of moisture stuck to the glassware. And if the humidity changes even slightly, then that could change the last digit or two of your measurement as slightly more moisture sticks to it or slightly more moisture leaves. So if a measurement takes too long, that could be a major problem. Okay. I now have all 4 measurements. So what I'm going to do now, obviously I'm going to do the rest of the analysis, but what I'm going to do is I'm going to take all these measurements and I'm going to put them in a PDF and post them online so that you can go and do the last part, which is the analysis yourselves. So go ahead and you're going to do the analysis yourselves and you're going to do the write-up, and then that is going to be that. Thank you for tuning in for the KoolAid density experiments. Bye.